Let's see, it worked. Okay, so I'm on the presentation. Let's see, it works. You should have told me that we're live.
Oh.
Well, hi everyone. I guess that's the time we actually need to start. So, hi everyone, and welcome to Kranky Geek, live event for 2021. With me today are Chad and Chris. Chris is he's behind the scenes, so the speakers see him. He's there on the chat, and he's going to continue to keep you entertained as we bore you to death here. Chad, can you show your shirt? Can you show? I've got the 2019 this time.
Yeah, I did my 2016. I actually couldn't find the 2015 one. I don't think I got one. We ran out of them before I had a chance to grab one.
I always grab them before everyone starts, and Chris chides me for that. Anyways, we're here for you, the Kranky Geek team. We're starting from scratch.
Start it over. Rehearsal.
Okay.
Live.
Hi everyone, and welcome again to the Kranky Geek event. We had a minor glitch. That's because we're doing these things live, so sorry about that. This is our 8th event and the second virtual event. With me today are Chad and Chris. Chris is behind the scenes, handling the things and making sure that we stay live at all times. Do you want to show your shirt, Chad?
Yeah, I put on my my 2016 one. I looked for my 2015 one, but I remembered we gave them all away before I had a chance to grab one.
I decided to put the 2019 this time.
Okay.
Sadly, we don't have a 2020 or 2021. Hopefully next year.
Yeah. It's not what we give out in person.
No. So if you want to tweet or follow us, go and do that through the Kranky Geek hashtag. And you can find the online schedule in the link below, or just go to krankygeek.com. This is what we're going to do today. There's a full schedule of a lot of sessions, and we're going to keep them fast-paced. A few house rules before we start. We're doing this live. Those who've been there from the start, this is the second time I'm saying that we're doing this live. You can stay in the live stream. There are going to be short breaks between the sessions. Okay, but the URL and the stream is the same. You can ask questions into the YouTube chat during the sessions. At the end of each session, we'll give a few minutes for Q&A, where we'll pick and collect the questions from the chat and ask the presenter these questions for you. You can also subscribe to the recording notifications on our Kranky Geek channel on YouTube.
Kranky Geek would not be possible without our sponsors, and we're fortunate to have another great round of sponsors for this virtual event. As always, we'd like to thank Google, who's been with us been with us since the beginning. In addition, we also have Agora, Dolby.io, Element, RingCentral, and Twilio. Now, before we proceed, I'd like to recognize one of our colleagues who recently passed away. As a technologist, a standards contributor, and founder of WebRTC companies, Dr. Alex was deeply involved in WebRTC since the early days. This picture here is actually of Dr. Alex speaking at the first Kranky Geek event in 2014. He was a frequent attendee of our live events where I know many of you spoke to him. We mourn his loss, but are thankful to his many contributions to WebRTC and thankful that his many contributions to WebRTC will continue to live on. Rest in peace, Alex. Before we get into the event, I'd like to quickly comment on what's happening with WebRTC. Well, WebRTC is an official W3C standard right now. We have WebRTC 1.0. Browser interop is getting better all the time. It was pretty good to begin with. We continue to make strides there. And more importantly, WebRTC continues to see a huge boost resulting from the pandemic. This has not only increased traffic, but also helped to push real-time communications into new use cases and new applications. And the community has responded to these demands with many improvements to the underlying technology. And these improvements have in turn opened up even more use cases, putting us in a great positive feedback cycle.
Then I guess that brings us to what it is that we're going to talk about today. We're going to start with a session from YouTube about game streaming, live game streaming that they're doing from Stadia to YouTube and the challenges there. We'll continue with a session from Element around call signaling in WebRTC and what metrics is doing and why. Then we will have Agora speaking about distributed SFUs and how to achieve low latency in a virtual network. Then we'll have RingCentral. They will speak about screen sharing and how to improve upon the screen sharing capabilities that are available out of the box in WebRTC. Twilio will talk about the mobile web with very good best practices of what you need to do with your application if you're intending to use that on the mobile web and not a native application. Dolby.io will talk about optimizing real-time audio for music-related use cases, especially the ones that are social or engaging or playing online with others. And we will finish off with Google, talking about Lyra, their new AI-powered low bitrate speech codec, and we'll learn more about it.
So we're doing something new for this live event. We're actually at the end. Make sure to stick around. We're going to have a number of breakout sessions hosted by our various sponsors. Now, in the past events, a lot of you have had questions, and please put them into the YouTube chat, as Yasai mentioned earlier. But if you have a question that you weren't able to get answered, or something more involved, or just want to learn more about our sponsors, you can join these breakout sessions. We'll put links to these breakouts in the YouTube chat, and we'll also send those out in email if you're registered already. So just keep an eye out for those towards the end. And make sure to make sure that you get notified. Make sure you subscribe to the channel. That's the best way to find out what's new and see the videos as they're posted and get other notifications, including new events. And with that, we'll conclude our introduction. We'll be back in just 1 minute with the YouTube team to talk about their live streaming.
See you in a second.
All right. Now I'm excited to welcome the YouTube team. Actually, we're using YouTube Live now for this broadcast, but this team actually has helped to bring live streaming for Google Stadia, which we've talked about in past events. So to explain more, I'll hand it over to Britt Sire and Ying Ying.
Hey, I'm Britt. I'm Britt. I'm going to present with Ying. We're going to talk about WebRTC Stadia live streaming to YouTube, how we take Stadia gameplay and send it to YouTube and broadcast it through YouTube Live. Today, we're going to talk about WebRTC, why it's unique in Stadia live streaming's use case, YouTube, compared to other uses of WebRTC we have, what makes it unique. And then Ying will talk about Turn as an ingestion proxy, why we need to use Turn and how we use it. And then we'll leave some time at the end for question and answers. So you're all pretty familiar with this WebRTC use case. Video chat conference, bidirectional, where we optimize for smoothness. The most important thing is that you don't ever get any buffering. You'll sacrifice quality, resolution, frame rate, bit rate in the name of getting quality. For live streaming, which we've done in the past with WebRTC, it's a little different. The ingestion side is unidirectional, so you don't have any feedback. You only have one channel that you have to get the audio and video through. You have to do adaptive formats. And you really want to optimize for quality. Stadia, it's a totally different thing, where we have two sides, gameplay to the gamer, and then we also have the YouTube side. So this is what our system looks like. The Stadia instance in the middle does WebRTC connection to the gamer on the left. That's bidirectional. That's very fast, low latency. That's interactive. And then on the right is the YouTube side, where we send live streams to YouTube with WebRTC, and we do our delivery. We don't use WebRTC there. We're going to be talking about the Stadia to YouTube part, the arrow to the right in the middle. So what's unique about Stadia? Well, for WebRTC, we usually do mobile live at YouTube, so broadcasting from your Android iOS device to YouTube. Those streams are a lot of just talking heads, a person just standing there with their phone out talking, very simple background, low bit rates, pretty easy to encode content. Stadia, on the other hand, is gaming. Gaming is high bit rates, high complexity. The content needs sharp text on it. You really do care about quality on that use case, where you don't in Stadia in mobile live streaming. On mobile live, we use H.264 because that's what's available on phones. Your Android and iOS devices have pretty good hardware encoding for H.264, but they can't really do anything beyond that too reliably. Stadia, it's operating in the cloud, so we can use VP9 or higher quality codecs like AV1. Right now, we use VP9. We have the extra compute we're willing to throw at it, so we can get better bit rates. YouTube Mobile Live, we use SDR. That's the standard color space. I'm going to talk more about color in a minute. Stadia, we do SDR some, but we also do HDR, so if you'll handle high dynamic range content. Mobile Live is 1 megabit on average. We'll go down to 300 kilobits, maybe a little lower, up to maybe 2 megabits. But we really stay in that low bit rate range, where Stadia, high quality gaming, 4K 60, it gets up to 30, possibly up to 50 megabits. YouTube Mobile Live is on cellular networks, so we have to worry about losses, adapting our quality, resolution, frame rate. Stadia, though, it's coming from a Google network. The Stadia instance runs in the cloud. We're sending to the YouTube cloud. So it's a near perfect network. So we really don't have to worry about losses, even though we have to deal with the 4K 60, 30 megabits HDR content.
Okay, so like no packet loss, I guess is what you're saying.
Yeah, we don't have to deal with much packet loss on that. But it's still tough to deal with high bit rates. So we'll talk about how we solved it, specifically the color issues. So for HDR, you have a few options. H.264 10-bit, no one really uses it, so you can ignore that. Your options are the newer codecs. So HEVC H.265, well, we can't do that because it's got royalties on it. We don't want to pay royalties. AV1, you can't really do that because not that many people can encode AV1 right now. So you don't want to rely on that. In the future, we want to use it, but it's not there yet. So that really leaves us with VP9. VP9 has a thing, VP9 Profile 2. That's 10-bit VP9. You negotiate that in the SDP. Here's an example of it. You can see Profile ID 2. When you set that, then you get VP9 Profile 2, which is 10-bit, can express HDR. So I can't really show you what HDR looks like versus SDR because you're not looking at this on an HDR monitor. I'm not broadcasting HDR content. But when you get HDR, you map it to SDR to look at, and you can see the difference here. The one on the left is gameplay SDR, what it looks like when you're playing an SDR game. In the middle is if you took HDR content, which is much more vivid, brighter, it looks generally better when you map that down to SDR to look at. And on the right, you can tell it just doesn't look as good because it's HDR content where we just treat it as SDR. It gets a lot duller. You can't really see as much definition. It's just not as good looking, but the middle one pops a lot more than the others because it was HDR. There are a lot of kinds of HDR though. So when I say HDR, there's a few different specs. There's a lot of them actually, and you have to know which one you're using. For us, VP9 mastering metadata gets included in the container in the color tag of WebM. That presents a problem though when we need to get the containerized video down to our transcoding pipeline is WebRTC doesn't have a container when it's on the wire. So we need to send this metadata across the WebRTC connection, and then when we containerize it on the other side, then we have to put the metadata on. So what metadata do we need? We need primaries, matrix coefficients, and transfer function. Primaries are probably the important one, the most important one. It tells you which color space you're using. So here's an example or an image that shows you different color spaces. The middle triangle is BT709, that's SDR. The next one is BCI-P3. That's a somewhat HDR color space. Apple likes to use it. But now the most common one is BT2020, that's full HDR. You can see you get more colors are expressed than they are in SDR. Matrix,
and those the axes are like a percentage of
their chromaticity. It's pretty hard to explain.
Okay, all right.
I
guess people can see the Wikipedia article if they.
Yeah, you can look up color spaces and you'll see these images. Yeah. And then just because you have 10 bits doesn't mean you can map every color that we want to see. So our displays go up to 10,000 nits generally, the very good ones. So that's 10,000 values you have to be able to describe, but we only have 10 bits. It turns out though that we don't need to be able to describe every possible luminance value because our eyes don't really know the difference. Our eyes are very good at differentiating very low light differences, but at high brightness, we can't really tell the difference. So these curves here show you the different transfer functions that we could use that tell you what mapping of an integer value of your gray code to a luminance. So most of the gray codes get mapped to the low luminance values because that's what we can perceptually tell the difference between. PQ is our favorite curve, perceptual quantizer. That's one we use, it's the red one. It just uses the vast majority of its bits are dedicated towards low luminance values. The place we set this metadata that we need is in the RTP headers. Most important stuff, the primaries matrix, we get that here. We also get the luminance, minimum, maximum, mastering metadata. That tells you mostly how you map your HDR to SDR. So if you have someone who wants to watch your stream in SDR, but you're playing an HDR stream, you have to make it available for them and actually look good. This tells you the proper way to map it down. So it tells you what the screen is made for rendered at. If you have a screen that can only play 5,000 nits, you don't want to get content that goes up to 10,000, stuff like that.
And you map this to, well, I guess to RTP, so you can change these values.
Yeah, so we put these in the RTP headers instead of at the beginning of the stream because we send this on every keyframe. So it could change in the middle of the stream. In practice, okay. That's HDR 10 plus. You don't really need to change the colors in the middle of the stream, but it is possible. It does happen in VOD, and we could look into doing it for live.
Okay.
If you want to use it, API video frame.h in WebRTC, you can see where you get it, where you set it. This comes in on the video frames. It's set on the very first one and on every keyframe afterwards, but you can get access to it on every frame. Then I'm going to hand it over to you to explain why we have a turn proxy for this and what it does.
Okay, thanks, Brett. So I'll first talk about typical turn server usage in a typical WebRTC application setup. And then I'll talk about why we use it as a live stream ingestion proxy. So turn stands for traversal using relays around NAT, and NAT means network address translation. Turn service is an important piece in most WebRTC-based applications when clients cannot make direct peer-to-peer connections. For example, in a typical video chat setup shown here in the diagram, the two clients can be behind firewalls, which is common for a home network setup. So in this case, the clients have their local IP addresses, but they need to send each other public IP addresses in order to connect. The public IP address is provided by the network address translation layer from the router, but the clients need to discover their public IP address. One option is to use a STUN server, which stands for Session Traversal Utilities for NAT. But this doesn't always work. For example, when the clients are behind a symmetric NAT, the public IP addresses returned from the turn server doesn't work in that case. So for that case, the clients will need a turn server that acts as an intermediary to send and receive data. And the turn server has public addresses, and they can always be accessed by all the clients. Now let's look at how this applies to the Stadia live stream ingestion use case. The Stadia instances running on the edge network have public IP addresses, so they are accessible by the clients. And they always try to form a direct peer-to-peer connection with the player client whenever possible. So the player client is the one on the left in this diagram. However, for the live streaming part, our live ingestion server running in the core data center does not have a public IP address. So they are not publicly accessible. And the Stadia live streams are not considered external traffic from our perspective because the external game developers control the game code running on the Stadia instance. So the Stadia instance can't form a direct peer-to-peer connection with our ingestion server. And that's why we need a proxy with public IP address in this case. So we consider different solutions. One option is to build a new UDP proxy that can forward the UDP packet to our ingestion service. Another option is using an existing turn service that Google already has for the video chat applications, such as Duo. So this turn service is high performance, it's written in C++, and can handle the high bit rate from Stadia live streams. And it's also already globally deployed. Whereas building a new UDP proxy from scratch will require significant development time and cost. And in this case, both options would require an intermediary service, so that's the same. The downside of using turn service, though, is it will require an extra 4 bytes per packet for the turn channel ID. But we think this overhead will not affect the performance, whereas saving the development cost will be significant. So in the end, we choose to use the existing turn server as the ingestion proxy. And it worked pretty well. We can handle high bit rate like 30 to 40 megabit per second with very low packet loss. So also on the ingestion server side, we set the ICE transport type to be relay only in RTC configuration. This is just an optimization so that it doesn't need to spend time collecting ICE candidates for direct connection case.
Yeah, that must be quicker. Do you have any idea how much, well, I don't know if you've measured how much time that saves, but it's got a...
in terms of?
I guess, connectivity time, that sort of thing.
We didn't measure, but yeah, we did notice that it takes, if it's like tries to like get other direct connection candidates, this does spend more time.
You get the advantage that you always know the turn relay connection is there, so you can when you default to that, like you don't have to wait for the candidate to come back.
Yeah, so that's it. Actually, that's the end of our presentation. We're happy to answer any questions.
Great. Thanks, Ying. And we actually did have a couple of questions come in off the YouTube chat, and I guess I encourage everyone else out there to ask their questions. Maybe while we're gathering up the questions, I have one quick question. YouTube also has a feature to go live right from a browser. How how would you compare your efforts in implementing that feature versus the Stadia feature? That's more of a peer-to-peer, what Britt showed in his original diagram. But do you find that one to be more complex, or was this one in some ways easier? I mean, it's different engineering challenges, but maybe less variable because you control more of the elements involved.
I would say it's not that difficult. I mean, what we're building here is based on what we already have for the normal web browser-based ingestion. So when we initially developed the WebRTC-based ingestion for webcam, there was a lot of challenges actually to make WebRTC work on the server side, because the library itself wasn't really made for server side actually. So we actually need to make some modifications. And once we have that, for the Stadia case, it's really about improving the performance. Actually, it's important to handle the high bit rate.
Okay. There was one question that came in about the packet overhead. Yes, is it 30 bytes for each RTP packet, or is that only for the keyframes?
Every packet, actually.
It's every packet, yeah. So is that a problem? I guess you're that additional bandwidth that's required.
So yeah, in this case, we didn't see any problem with that.
Okay. Some other questions asking, like, do you use Turn as part of Kubernetes? I guess some questions if you can elaborate a little bit more on what your Turn infrastructure setup looks like and how you do that.
It doesn't use Kubernetes. It is still, it's running on our normal like Google data centers. It's deployed both in core and edge networks. That is also, I think, the important part. Like it really needs to be deployed widely close to the edge in order to have good performance.
So, have any other questions?
I think that there were a few, but we need to start preparing for the next session.
All right. Yeah, unfortunately, we need to wrap up here and join our next session. But thanks so much, Ying and Britt. This was really interesting.
Thank you for the opportunities too.
All right. See ya.
Bye.
Okay, we're back. For those of you watching the live stream, I guess there was a little mishap here. We'll restart again. One of the bigger challenges of WebRTC is signaling. WebRTC doesn't include signaling, so you kind of need to figure that on your own or work with a partner. And one great project to use actually is matrix.org. So to talk about that project and how to use it and how signaling can work in WebRTC, I'd like to introduce Dave Baker. Dave, take it away.
Thanks very much. By way of a quick introduction, my name's Dave. I work for Element, which is the company that mostly develops and contributes to the protocol development of Matrix. I've been working for Matrix since the start, across most of the stack. Started off my career writing C++ for media and RTP stacks, just sort of a general introduction. Well, I thought what we're going to talk about today, basically I'm going to talk about WebRTC and, as Chad was referring to, the fact that there is no signaling layer, and tell you a little bit about Matrix, about how the events work, how calling in Matrix works, a couple of problems and how we solve them, how we do E2E in calls, and then just the openness of the standard. Let's kick off. How do you set up a WebRTC call? I suspect most of you probably know this. You probably all use the API. You do things like adding your local tracks, you generate an offer, you send the offer to the other side, and then you send candidates to the other side. But how do you do that? Well, most people, you probably use an HTTP call or a WebSocket, open a WebSocket, send it to the other side, the server in the middle. It works pretty well. But what if there are an open standard, something like SIP, but a modern version for the web? That's what it looks like at the moment. WebRTC includes those bits. SIP was not part of it, which is probably a good thing because SIP is quite old and most of it is based around UDP and retransmits, and the retransmits that you need to do to make it reliable.
I assume the avian carrier example you had there too had similar limitations. So.
Yeah, pretty unreliable by and large. So Matrix, what is it? It's open. It's we got modern standard for real-time communications, which means it's open. So all the client servers are open. It's open source and it's an open standard. It's federated, which means I can host my server and you can host your server, and we can both talk to each other. We don't need to be locked inside a walled garden or a silo. It's completely extensible. All the events are JSON based, and you can basically put whatever data you like over there. And there's end-to-end encryption available, which I'll touch on a bit later. There are lots of different clients available. I obviously work for Element, who writes the client called Element, but you don't need to use that client. You can use your own client if you don't like Element, and you'll get just as much access to the Matrix network. A few use cases, obviously, we'll be talking about that first one, interoperable VoIP. Here's a general overview of how the ecosystem works. There's lots of clients up there. I'm not going to go through the whole of this diagram, but that should give you an idea of everything that's out there in the ecosystem and the stack and how everything fits together. But there's three different types of element. There's an experimental client called Hydrogen, and then there's lots of other clients that are all open source. In terms of adoption, VoIP has been back in Matrix since way off the end of that graph in 2014. And now in 2019, 2020, we decided to give VoIP a bit of an overhaul and make it a bit more robust and a bit more reliable. So Matrix event, what does it look like? It basically looks like this. You can see there we've got a type and some content, and then in that content is a body. And then we've got a sender there. That's me. I'm Dave. I sent this message. And the room ID is the ID of the room that this thing's in. So there's another me talking. Let's see what this actually looks like in the wild.
Cool. You got a demo here?
I have, yes. So this is Element. This is the web version. This is the developed version, in fact, development.element.io. And this is me. This is me saying hello world.
And it is all open source stuff too, right?
Yes, it is. Yes. Say hi, Kranky Geek. So I can go have a look at this in our developer tools. I can view the source of this message. There you go. It's got a body. Things like the timestamp, which is right now, the timestamp that was on metrics.org. and the event ID. So that's the very basics. What about calls? Basically, they look a bit like this. You send first an m.call.invite. You can probably guess what kind of things these do. And then if you're familiar with WebRTC, you'll know that there's a thing called trickle ice, where you can send your candidates out as they're ready, which means you don't have to wait till all the candidates are gathered. Your call can connect faster. Matrix supports those right out of the box with the mCall candidates event. I'll tell you a little bit more about that later. But for now, here's the invite event. Not much to it, really. It's got the SDP there, which is the SDP that comes straight out of your WebRTC stack. It's a type offer, and there's a call ID. There's a couple of other things that I'll go into a little bit more detail later, but we'll leave them for now. There's the candidates event. You can see the candidate there. That's just one candidate. It's a relay candidate. That's probably well, I made that one up, so it's probably not actually.
Yeah. Well, we just talked about turn relay in the last session. So
yes, so we're all experts on that now. But yeah, that's what it looks like in Matrix, and that's just sending a single candidate over. So let's have a look at this in action as well, shall we? There's that client back, and there's another one. So I've got somebody to call, and let's try a voice call, shall we? There we go. And I'm in developer mode here, so you can see these events come in here. I'm going to mute myself so I don't get hell around. But there you go. I'm in a call now. Actually, hang that one up now. Let's prove the point. But yeah, let's have a look at this. There's the SDP. It's all of it. It's only half the length that it would normally be if it was a video call, but there's still quite a lot because this is.
Well, the fun parts of WebRTC, the SDP. So
yeah. And then you can see there's candidates again. There's going to be a lot of these. Lots of candidates. So yeah, and then you can see that I've not got developed. This is what it looks like if you don't turn developer mode on. You don't see any of this. Yeah, that's basically what a call looks like. So, what's a little bit more about the subtleties? What kind of problems do we run into, and how have we worked around them? Well, it's important to remember that in a protocol like SIP, you would always be sending these signaling messages to a single device. Whereas in Matrix, everything goes to a room, so everything's seen by all users in the room, which if you're just calling somebody directly is just the other user, but you'll still see your own messages, in fact. And in fact, you'll have multiple devices. So you might pick up or call somebody, and then they'll pick up the call on one device, and then they might decide, oh, well, I want to pick it up on this device instead. And the way we work around this is we have this concept called party IDs. That's it there. You might have seen it in the previous event, but it's highlighted there in red. And it's pretty simple. At the start of the call, you just pick an ID for your device, or you just use the device ID from end-to-end decryption, as long as it's consistent. An ID for your party in that call.
Okay. So each device gets its own party ID?
Yes. Yeah.
Okay.
And then that basically just allows us to match up the candidate's message from each device to the answer that they sent, because we couldn't do that before. And that's a thing that's new in the new protocol, actually. There's another problem, which is that if you do get that problem of multiple devices trying to answer, the callee will pick one of them, but the device that didn't get picked won't necessarily know, and so it will sit there with media not connecting and not knowing that it hasn't been picked. So we invented a new event for that, which is called the select answer event, which is just an event sent by the caller to say, hey, I picked this answer. So if you're the device that it didn't pick, you'll see this in the room, and you'll see that it didn't. Let's say you're Bob 2.
Okay, and then you could stop ringing or stop whatever notification, right? Okay.
Yeah, exactly. You can just close down the call interface and get back on with being a client. So a bit like that. Probably broadly what you would expect. It's got a call ID and it's got a party ID, and it says and it's got a selected party ID, which is the ID of the party, obviously, which the answer you picked. Couple more features. Now we've got negotiation. So WebRTC, you probably know, it has this negotiation semantics. So if you want to change the SDP during a call, it's often used for hold and resume functionality, things like that. We can do that now right natively in Matrix. You just send this m.call.negotiate, the type offer and a type, and then you respond with a type answer. Looks a little bit like this. I've highlighted there in the SDP. You can say that. See, that's A equals send only, so that might be putting somebody on hold, for example. Other than that, looks very similar. It's got a call ID, it's got a party ID, as we saw before, and that's basically it. Should we see that in action? Let's try this on. Here we go. Right, here are two devices again, and again, I'm going to place a call to Dave Test 4. There we go, and they're ringing. So here I can put me on hold. There we go. It's updated to show that I'm on hold, and you can see these two m.call.negotiate events. Again, the SDP is a normal. Somewhere in there's probably an A equals send only. You probably have to trust me on that unless you can find it. But there is. It's a type offer. That's the point.
Okay.
It's doing this negotiation. And then you can see the other party is sending this type answer. Can also do if we're... why not? We've got another one. This is Dave Test 3, and I can actually get this one back. So I'm going to show you now. I've got my Android device here. So let's try calling that. This is Dave Test 3. My Android device is signed in as Dave Test 3. So let's try calling, and with any luck, I'll be able to, yep, my Android device is ringing. I can answer that. And yep, correctly, that has indeed stopped ringing here. So it knows that it's the call's been answered on my Android device and it can go away. Now I've got a call established between this Android device. Same works on iOS, could have showed you there, and this browser. And that's Element on web and Android. So you can just switch between devices seamlessly.
Cool.
There we go. So I promised I was going to tell you a little bit about E2E. Here we go. So in Matrix, all conversations are E2E by default. So if you don't do anything, if you just start a conversation with someone, you'll be using encryption and your conversation will be secure. We also have verification. If you actually verify someone, then you can absolutely guarantee that they haven't been man in the middle by anyone and you are genuinely talking to that person. But you don't have to verify people, and then you get a reasonable level of security. Bit like any other encryption protocol, really, any other messaging protocol. It uses OLM, which is our double ratchet algorithm. That's for single device to single device. And then MEGOLM, which is the group ratchet, which ties that all together to do conversations between large numbers of users and large numbers of devices. Won't go into too much detail about that. MEGOLM makes it a little bit faster, but decentralized MLS, which is not a Matrix standard, but a general standard. We're in the process of implementing that, and that gives you logarithmic performance with respect to the number of devices in the room, much faster. WebRTC uses, as you probably already know, DTLS encryption, and basically the theory of that is that if you get this fingerprint to the other side, then you know that your call is secure, and you know that it's not being intercepted. The benefit of Matrix is that you put that in a message in an E2E encrypted Matrix room, and it gets the same level of protection as all of your Matrix messages get, and you can guarantee that it gets to the other side and it hasn't been intercepted, and you can check all the signatures will be checked transparently in the background, and you know that your call is secure. So basically, if you make a call over Matrix in an E2E room, and you get E2E encryption for free. So just quickly at the end, a little bit about the standard. It's an open standard. Those are the Matrix spec changes there. You can go comment on them, you can read them, whatever you like. It's an open standard. If you don't like it, you can change it. Or you can, or better still, you can tell us how we can change it. So yeah, just a couple of words in conclusion. Yeah, we built WebRTC right into the core of Matrix, and calling on Matrix will continue to evolve as WebRTC evolves, and it's hugely powerful. Everything's open. File bugs, make comments, make MSCs. Yeah, always love people to get involved. So yeah, thank you very much.
Great, thanks, Dave. I think we do have a minute or two for Q&A, so I'll let you read them off this time.
And we do have a few questions. The first one is Matrix supported by VoIP providers?
So it's not actually supported by any VoIP providers that I know of at the moment. We are making bridges. So obviously it's possible to bridge between Matrix and SIP, which most of them support. So you can bridge that way. Unfortunately, it's not supported. Yeah, hopefully one day it's, well, everybody go and ask your favorite VoIP provider to support Matrix.
I think I'll go now to the other part, and that for me is one of the main strengths of Matrix. This is the person asking that said that it's a dumb question. It's actually a very good question. So you can have different client vendors message each other over the Matrix networks, but am I right that you can run different instances of a Matrix networks as well, all working together?
Yes, yeah. So different clients connecting to the same home server, and also different home servers all talking to each other.
Okay. Yeah, your home servers can federate with each other. You have a
Yeah. So if, say, I don't know, Microsoft ran a home server, then yeah, I could with my matrix.org address, I could talk to someone on Microsoft's hypothetical Matrix server, and that would work.
Mm-hmm. Okay. Does Matrix include the chat messages in the signaling it provides, or is chat relayed isolate from the signaling channel?
It all goes into the room. So everything, when I showed you the event that was me saying hello Kranky Geek, that was just basically a message that went into the room, and the signaling is at the same level. Basically, is just a different type of event. So everything goes into the room. So when you're calling someone, you make a room with just you and that other person, and then you send a call invite into that room.
Okay. I'll do, I guess, one or two more questions around forking, and then we'll.
Yeah, actually, so we're.
Okay. So the last question.
We're 1 minute away. Yeah. So one last one.
The party ID session. Is it based for life of the device, or is that changed per session?
In Element, it is the life of the device, because it's tied to the device ID, which is a fairly easy way to do it. It doesn't have to be, though. The Matrix spec says as long as this remains the same for the lifetime of the call, you can change it between calls if you want, which you might want to do if you don't want people to know what device you're answering calls from.
Okay.
All right. Unfortunately, this was great, Dave. Thanks so much. We'll see everyone in our next session in just about a minute or two.
Sure. Thank you very much for having me.
One more thing. If you have more questions to Dave, he will be in the breakout room at the end of our Kranky Geek event today. Okay, so wait up and join there.
Live streaming is on.
And
Okay,
you
well,
collect the questions.
Yeah, and I like keep the until I think we've seen that people like the chart, so you're doing a good job here. Okay,
I think sorry, the last one. I think maybe I forgot to turn on this. Everyone follows me.
Yep.
At the beginning of the session. Crap.
That's fine.
You're live, Bill.
You're still here. Okay. So hi everyone again. With me now is Ben Weeks from Agora. Ben has been within the WebRTC community for many years. I've seen him in previous events, not the Kranky Geek ones, though in Forma, I guess. And he's going to talk today about distributed SFUs using virtual networks. The floor is yours.
Thank you, Sahi, and hello everyone. I'm Ben Weeks, and I'd like to show you how to run WebRTC video calls with better quality and scale than I realized was possible until recently. Have my slides disappeared? I can just see myself.
No, that's fine.
Okay, cool. So first, a quick look at some old photos. This is me back at the very beginning of WebRTC, nearly 10 years ago. And I've been heavily involved with the technology ever since. But only in the last year have I realized that some of the fundamental architectural assumptions that I've held firmly in my head are not entirely true anymore. And let's have a look at those. So I used to say things like, you've only got 2 people in the conference, you might as well go peer-to-peer, the quality would be better. Or I'd hear things like, they're using a VPN, no wonder the quality sucks. Or a single SFU placed geographically in the middle of a group is going to give you better results than a distributed SFU or bridging where you've got extra hops involved. And all of this has turned out not to be the case, actually. So let's have a little look at a simple peer-to-peer call between someone in London and someone in India. It looks like the packets are going to go the shortest possible distance, the shortest path. And on each end, you've got the browser doing its dynamic bandwidth adaptation and calculating the forward error correction and giving you the best possible experience for that line of packets. And whatever you're going to do, the people are still going to be on the same internet connection at home, regardless of what you do in the middle. That's the kind of thinking that I used to have. And if I was to put an SFU in the middle, that's only going to make things worse because there's an extra hop and I'm stopping the browsers from having that direct end-to-end ability to calculate the bandwidth and to calculate the FEC. So it's only going to be worse. This is the best you can possibly have. But it turns out that that's not the case. And I'm going to quickly show you what a better architecture looks like and then give you a demo of it. So what we have here is an SFU placed in the IP network of the ISP at each end of the call, and a couple of SFUs in between, which are routing the packets over the most optimum path between those 2 users. And I'm going to give you a little demo now, which I recorded just yesterday with a colleague of mine. And before I press play, let me explain what's going on here. On the left, I've got a Chrome window with WebRTC running. So our browsers have exchanged SDP and we're running over the public internet peer-to-peer. And on the right, another Chrome window, and we're both in an Agora channel. And Agora are operating the architecture that I just showed before, which they call SDRTN, or Software-Defined Real-Time Network. And now let's look at the 2 in action. You'll hopefully hear the audio from the video, and I'm basically going to ask my colleague Vineeth to move his hand, and everything in this test is exactly the same. We've got the same network, the same internet connections on each end, the same devices, the same browsers. The only thing that's different is the public internet versus Agora's real-time network. Okay, press play. And one more time, put it up to the middle position still. And quickly down. Brilliant. Oh yeah, do that one more time. It's really good. Into the middle and still. Down quickly.
It's incredible. It's almost a second quicker. All right. Thank you very much, Vineeth. Have a good day. Speak to you soon. Yeah, thanks.
So just a quick one question then. So these are two screens running at the same time on his side and yours. You're just opening it in two browser tabs, and he's doing the same.
Correct. Yeah, you could just about see the URL bars of the two. You've got WebRTC on the left and an Agora demo page on the right.
Okay.
And then below each window, I've got WebRTC internals, so showing the round trip time for each call. And for the public internet, it was moving from between 200 and 600 milliseconds round trip. But for Agora, it was pretty much a constant 15 milliseconds. And that's because I was talking to an SFU in my own ISP's IP network. Yeah, it's the shortest possible distance, basically me to my ISP. And then everything else was taken care of by Agora. And at the other end, exactly the same for Vineeth in India. So I'm now going to try, oopsie, get the right screen here.
And one more time.
Oops, like here we go. So I'm now going to explain what's going on the internet, which is kind of the stuff that I wasn't overly aware of perhaps in the past. So at the bottom, these yellow circles are people connected to the internet, like you, me, and Vineeth at home. And we're generally using tier 3 ISPs. And those tier 3 ISPs are using tier 2 ISPs, which tend to cover bigger regions, countries. And they in turn are using tier 1 ISPs, which cover great big, which are global in scale. But these are run and operated as businesses by different companies. So they've got their own costs and they're in competition with each other to a certain extent. Well, to a massive extent. And it turns out that an ISP's priorities of routing traffic are to go, as you can see here, over their own ISP network, and then to use free peering with other ISPs, and then and only then if they have to pay for transport. So you end up with lots of strange cases on the internet, like this one, for example, where if you're sending your packets from Mexico to Washington, DC, it's not very far in distance. You'd want to be able to take the green arrows. But what happens in practice for the major ISP out there is you end up sending your packets via Russia because it's the ISP have the agreements with each other, and that's the cheapest way for it to flow. And not only is it a longer distance, but it's a much more congested route to be taking. Another thing, this comes from the Thousand Eyes 2020 Cloud Performance Report, which I can't recommend enough. There's a link to it in the appendix of this presentation, which you can look at. But it shows that Google GCP, Google Cloud Platform, doesn't actually have a direct connection between Europe and India. So if you're transmitting packets that way, they'll go all the way around the globe the other way. And I picked on Google a little bit there, but the report actually points out that all 5 of the big cloud players have different regional anomalies, where they each of them have got certain issues depending on what region that you're in. Some rely heavily on the public internet in places. AWS have something called Global Accelerator, but that itself is worse than the actual internet for many connections between their different availability zones. All of these guys have a performance hit for in and out of China. And all these points are the summary of the actual report that I'm referring to. And the last one is that even in the US, the ISP that you're using makes a difference on your connectivity to the different clouds. So if you're operating WebRTC conferencing in one particular cloud, you're going to be subject to all of these issues from different parts of the world. When your users are in different parts of the world or on different ISPs in your own country. So what's the solution? It's actually to put SFUs into every ISP IP network around the globe so that you can connect your users directly on the fastest possible link possible, and then to send traffic between your different SFUs so that you can take the premium routes rather than going with the rest of the internet. And this shows that in action. And not only do you send your packets over one primary route, but you can send them, and the way that Agora works is you're sending them over 3 at one time. It's using machine learning to predict the best paths, and it's continually monitoring those paths in real time and able to switch them in real time to provide next to 0 packet loss between any 2 places in the world at ultra low latency.
So it's not just mapping the geographies and then deciding what to send by taking a snapshot. You need to, maintain that and dynamically change it as the network changes.
That's right. Continuous monitoring and probing of the network and the routes available.
Okay.
And what this achieves in summary is speeds twice the speed of the public internet. But people have completely varying speeds, but on average it's twice the speed. But more importantly, all of your users have a much more consistent speed, which is half of the average speed. So everyone in the conference is playing fairly, it levels the playing field, and everyone's seeing and hearing things at the same time. And you have close to zero packet loss from anywhere to anywhere in the world, including in and out of China. This architecture also lends itself really well to solving another problem which is common in conferencing, SFU land. So this is that single SFU that I described at the beginning, which works well in this particular scenario. But when you add a couple of people from over here, their voice is having to be sent all the way to East Coast and back just to hear their friend who's not that far away. And that's not a very good experience. But with SDRTN, or what's also called an overlay network, all the packets are taking the most efficient route to all the people. And then the challenge becomes here is to not duplicate everything and to send the packets between different regions only once, and then to be able to multiply those on those different SFUs and the various different SFUs. And the other beauty of this architecture is it sort of scales indefinitely, but Agora tests up to 1 million people in a single conference, which blew my mind when I joined, but it's all true and it's properly tested. So you can have up to 1 million people in a conference like this, all with the ultra low latency that I've been describing. And if you're a developer like me at heart, then you can rely on having a really good network which scales really well, and focus more on the more satisfying CSS things for building beautiful big grids which run beautifully in web browsers. And there's plenty more data at the end of my report, but my presentation, but I'm going to stop there and invite any questions.
Thank you, Ben. Chad, I saw a few questions on the chat.
Yeah, we got a few here. I think one was going back to your demo. Looks here as a question on like WebRTC. Was that going through an SFU versus going peer-to-peer? Can you explain like the architecture differences there? Yeah, I think you were showing a peer-to-peer versus versus network, and basically the
sorry. On the left, WebRTC was pure peer-to-peer. It was exchanging the SDP between my Chrome and Vineeth's Chrome, and then it was just using the public internet peer-to-peer to connect. And as you saw, it's not what you expect. It's not what I was expecting, but it's way behind going through a real-time network.
Okay. There's also a question of maybe more comment. What does the difference look like? It certainly seems to be more plausible when you go over larger geography. There's going to be a lot more differences. Do you see? Is there any limits to like if it's just someone staying within a certain region or within a certain country?
Yeah, and like it shows in that Thousand Eyes report, even in the US, depending on what ISP you're connected to, you've got different access to the different cloud providers. So you do, even in a particular country, see improvements. And what you tend to notice, even though the latency for people on good internet connections is the same, you don't have the variation where people on different ISPs have different amounts of latency and packet loss. Everyone's connected with exactly the same quality.
Okay. And do you see, I guess, how much of this is impacted by a lot like last mile factors? You can't control someone's Wi-Fi or, maybe the local ISP. So how does that compare to the overall latency budget, I guess?
Yeah, you can't help people's Wi-Fi networks in their homes, but what you are doing here is by having a point of presence, that's the right word, in every IP network, which is quite a big challenge. But if you know how they all fit together and you study and monitor it, and there's ways of doing that, you make sure that there's an SFU in pretty much every ISP around the world's IP network. So that last mile problem is the best quality that ISP is offering to their customer. So if you're on an ADSL, then yeah, you've got the same limitations that everyone that you're going to have with anything. But it gives you the best possible service that can be had on your internet connection at home.
Okay, I think we have time for one more question.
Yep. Yes, we do.
So there's some questions around, does this need to be within every ISP to be effective?
The way that ISPs get their internet connectivity from tier 2, that's the sort of relationship that you need to be aware of. And there's lots of different sharing. So it depends on the ISP, but generally all the important ones are covered globally. But there's over 300 points of presence. So that would be in different, all the different cloud providers. Some of it's co-hosting. There's a whole range of ways of getting into the different ISPs. But yeah, they're all covered.
Okay. Thank you, Ben. That was really interesting. And the fact that we need to optimize and decide where to place our architectural pieces in order to build a network and to improve the quality is really important. So thank you for that.
Thank you.
Everyone, Ben is here. So at the end of the event today, he will be in the room provided by Agora in the Berkeley room. So you can go there and ask the questions that we couldn't handle in this session. We're going to have a short break now, and we're back within 13 minutes or so.
Thank you.
Live streaming is on.
Hi, everyone. With me now is Arno Budkiewicz. He is the Senior Director of Video Engineering at Ring Central. For those who don't know him, he's been with WebRTC from the start. He's a true WebRTC pioneer. I guess that I've seen him in every meeting and event that I've been throughout the years. I remember the first product you've built, Bistry, and I know that you've built from that 5 different separate products that are WebRTC based. So Arnaud, the floor is yours to guide us through screen sharing.
Thank you, Tsai. Thank you for the warm intro. 3 years ago, I joined Ring Central, a Gartner leader of the Unified Communication as a Service business, with the offering message, video, phone, MVP as we call it. Let me ask you a very simple question. Does everyone can see my screen right now? I'll take this as a but I have bad news for you. Which is, screen sharing is broken. If you look into the details, the flow of the experience for an end user, especially if it's for the first time, the picker UX where you select what you want to share is clunky. Sometimes you can share audio, sometimes you cannot. As a user, I have no idea what's happening. The notification bar is in the way, share on both sides of the screen. And also, you have the infamous Hall of Mirror if you don't pay attention to it. So how to make screen sharing great again? First, as an application developer, enhance your desktop experience. That's something you control 100%, and you can modify as much as you want. Then work hard on the performance, because screen sharing is hard to do at high resolution and high frame rate. And so you will need to iterate for a very long time. And then once you have fixed all the major problems and you have your great desktop experience that you have as vision, then contribute back. WebRTC, WebRTC, Chromium, Firefox, WebKit. Go back to the community, discuss these problems that you solved, and help the community to have better products for the end user. So I'm going to start and go into the details with the confidence, right, that you need to bring upfront before the user will start sharing. So picker, that's the little window where the end user will select what he wants to share. And the problem that we have here right away is, okay, I have these different screens that I can select and I can recognize thanks to the thumbnail that are shown here. But what if I want to share just an application or just a tab? Well, I have no idea as an end user. Of course, we all use these different products, WebRTC based, for years. So we know that these are tabs. You click on it, but the first-time user has no idea. And then he wants to click share on the bottom right of the screen. And actually, there is nothing that is selected by default. So there is 2 extra clicks before to start and be successful with your screen sharing. You need to select first what you want to share. You need to select explicitly share. And if you hit enter, guess what? It's gone.
Yep.
Some people like to do this.
Happens to me all the time.
It's very annoying, and to be honest, it's very simple to solve. Right, it has been solved by many products that are native based, and this is the desktop experience that we built with Ring Central. So screens and application are in one single screen. There is no tabs. There is no extra click required. The screen number 1 is selected by default. And so if you click share, there is only one button at the bottom, right? You share right away. If you hit enter, it works, right? So not a complex problem to solve here. This is just UX.
So this is not something that you've done in the browser, right? This is something that you've done in the native application.
Correct. So we support both. We have the web client and we have the desktop client for Windows and Mac. And this is the desktop experience where we have full control.
Okay.
So confidence before you share, confidence while you share. So question is what I'm really sharing today. In the browser, you have the non-customizable notification bar. It's in the way of presentation material. You can move it around if you know that it's possible. You can hide it, clicking on the little, button that doesn't exist on the right. If you do this, there is no way to get it back. So this is, I think, an okay experience for the browser, but it has been changed for like 5 years, and I think we should rethink that. The Hall of Mirror, obviously, as an application developer, you want to make sure that the end user understands what he's sharing. If this particular window where you show to the end user what he's sharing is too large, you have this Hall of Mirror effect, which is very, very confusing for the end users. Okay, so what are you really sharing? On desktop, where we have full control again, what we've done is, you share your entire screen or you share an application, same thing. You have a green halo around what you share, and you have a little notch at the top that you can see here that is always visible and that is removed from what you share. So green halo and the notch are removed, and it's very easy to find this red button to stop sharing. Again, nothing fancy here, but it works. Multiple products over the time have been, going for this approach, so it's well known. But I really wish we would have that in the browser as well. Hall of Mirror, it's a very tricky problem to solve. We've been through a number of iterations, and in the end, we decided to remove the application that actually shares the control and shares the video that you are currently sharing on the screen. So this particular window is removed. If you remove something and the end user has no idea what is behind, that's potentially a problem. So that's why we also reduce the form factor of this window to the minimal. So you don't want to share what is behind. Here it's mitigated.
Mm-hmm.
Okay, now I'm sharing. I want to have control over what I'm sharing. What is the viewer experience? So you can try it by yourself, having in one screen both what you're sharing, the participants, and control your experience at the same time. It's very difficult. You need to use tab sharing, start slides, present to view, exit full screen mode, adjust windows. I mean, it's just nuts what you need to do. And there is no annotation on the full screen. So with the desktop experience that is significantly improved, you have full control. This window that I just talked about is it's customizable. You can make it bigger, so you can see the three main participants, and you can, if you click on the notch on this little crayon icon, you can start annotate, and everyone will be able to annotate on your screen. So for collaboration, it's very critical, right? Here, you control your experience, you control what you're sharing, and people can collaborate and be on the same page, annotating on the same content. Let's talk about the implementation here. I'm sure everyone is curious about how we managed to build that. So first, we started with a vanilla Electron, meaning no touching of Electron whatsoever. Chromium for Electron, for the one who don't know, that's Chromium plus Node.js, the capability to create an application that you can install as an end user on your computer, Mac or PC, and then have the benefit of native apps. You can have C++ code that are running and have access to the system and can do anything that the system can offer. What you see here is the complex architecture within. You have Node.js, you have the capture as a native module here, and then you have the frames flying around from this capture to the web app in a canvas, and then you have a copy here, and then you send that to WebRTC, and it's not very efficient. So the pros are no Electron, no WebRTC, no Chromium patches, which is okay, that's easy. It's easy to upgrade, so that's great. Cons are, a lot of unneeded code. You need GS wrappers, callbacks, timers. The logic is scattered between different pieces that are in different technologies, C++ and GS. It's very complex to maintain and to make it working at an interesting level of performance. Modify Electron, that's the next step. When you understand all the different pieces, what you need to do, and the performance is right, then you go one level deeper. And you're not afraid of having your capture as a C++ model within WebRTC, right? Within Chromium, within Electron. So you fork the entire onion, as I call it, but the performance are, very interesting. I'm going to show that in a minute. Pros, so it's a full native implementation. It's executed in the main process, so there is no JavaScript engine involved here. There is no throttling of any JavaScript process. You can expect a very much better image quality. And if there is any cutting edge contribution from the community that you want to leverage, that's totally easy for you to integrate. Cons, well, maintenance, the WebRTC patches, and custom Electron builds. But for an organization for us, like us, it's not a problem. So let's talk about performance.
Wait, before that, so you took libWebRTC in that case, you customize that, so you need to compile WebRTC, you need to compile the browser on top, Chromium,
Correct.
and you need to also compile Electron in a way.
Yeah.
So all of these pieces you now maintain on your own.
That's correct. That's correct. But if you go into the details of the build process, you can potentially build any version of Electron with any version of Node.js or Chromium. So you don't have to, have a super complex build mechanism at the Electron level. It's kind of okay to pick and choose the versions that you want.
Okay.
Performance. So it's my point number 2. You need to iterate a lot. That's the reason why we started with the vanilla Electron, and then we customize the entire architecture. So on Windows, this is what you can expect to get. So different performance for screen and window. So the content is important. The resolution is important. The work that will need to happen behind the scenes is critical. Again, remember that frame by frame, we remove this little window of the application, and we share the rest, what is behind the scenes. So we compose the view that we want to share, and we do this frame by frame. So with the native capture in vanilla Electron, we are, pretty high, beyond 50 watts of power. If you look at Chrome, which is the target, I would say, because you don't modify anything, that's twice of that. So the price is very high. With the custom Electron, we are very close to Chrome. So that's exactly where we want to be, right? People wouldn't understand that your performance on browser and your performance on desktop are very much, different. They want the same. On Mac, even a more drastic difference. But yeah, the native capture on vanilla Electron is pretty much at the same level of Chrome. This test has been done on M87. The stable now is 90, but this part hasn't changed much. So I would expect exactly the same performance. So what's next? Browser-based, our browser-based client. Available to anyone in starting from M90. You have everyone, the new codec that we've been waiting for such a long time. it's very efficient for screen sharing in particular. There is a footprint that we will need to carefully measure and tune, but we believe it's the future. I saw a lot of requirements from the community, from the end user, to share a portion of the screen. So it's already in discussion at the WebRTC, where RingCentral is member and I'm the AC rep, the representative. So I think it's an interesting problem to solve. Again, share a portion of the screen. It's providing more and more control to the end user and bring confidence and security. So I'd love that. Speaking of RingCentral, this has been announced yesterday. We are very proud of this overlay mode, where you can have in one video stream yourself in video and the content that you're sharing. So it's called a weather person visual effect. It helps the presenter to hold audience attention, and also the audience will keep an eye on the presenter and on the material that is presented at the same time. So really excited about that, and very proud of the different teams who work on this implementation. That works actually on web and desktop. So we are using cutting-edge technology here, and on web and desktop, we deliver exactly the same user experience.
Thanks, Arno. I guess it's time for the Q&A. Chad,
Yeah,
what do you have for us?
we have a few questions. There was one question, basically, what's the effort like to modify Electron? Is that something a small team could do, or does it require a lot of effort?
It's not a small team effort. It's multiple teams involved at RingCentral. Our product is very complex. Again, you have message, video, phone, everything in one app. And so that's multiple teams with different expertise that are involved in building all that. So it requires, a lot of people, and it's not a small team effort, in short.
Okay. Another question, is it a struggle for users? I guess, how do you deal with users like having a different screen share interface between web, I guess maybe between different web browsers and now your native app? Do you have any tips for dealing with that?
Right. So, like I said, the next step is really to contribute. So we already talk at WebRTC of all these subjects. We talk directly to Google and Microsoft for Edge, and Firefox, and also WebKit, Apple Safari. So we already fixed some issues that were blocking the experience a few releases back, and for 5 years in a row, you couldn't share PowerPoint or Keynote, go to presenter mode, and have this working. So we put a significant effort to fix that, and it's a contribution, and it's available to any developer, to any user. And we'll do exactly the same thing for all the different part of the UX that I mentioned.
Okay. Look some other ones here. You mentioned 15 frames per second or 30 frames per second. How do you manage, I guess, trade-off performance with the frame rate, and how you choose the right frame rate?
Right. So with a desktop app, you have access to the information about the system. So we monitor the system resources that are used, and we adapt to that automatically.
Okay, so you automatically adjust rather than just setting one.
Last one, I think, Chad.
Yeah, I don't know. I see a bunch of comments of people complaining about Zoom and other things. I'm not sure there's any questions other than lots of complaints.
So I guess those that want to complain or to actually ask questions and understand what exactly RingCentral did, there will be a breakout room, and at the end of the event, Arno will be there. You can join us and ask him directly. Thank you, and we'll see you in the next session in a few minutes.
Live streaming is on.
All right, welcome back, everyone. Certainly, a big topic is mobile. And then we've actually had a whole event almost dedicated to mobile. It certainly hasn't gone away. I think one of the more interesting aspects of that is how the mobile web has evolved itself, right? So, do you actually even need a native mobile application anymore? Can you get away with a mobile web? So, to talk about that topic, we have one of our sponsors, Twilio, and Donald Toomey. Donald, I'll let you take it away.
Hey, thanks. Thanks, Sahi, Chad, Chris, for having me on the show. Delighted to be here, long-time watcher. Today, I'm going to talk about best practices for developing WebRTC applications on mobile browsers. So I'll talk a little bit about the mobile browser growth that we've seen, some of the challenges with mobile browsers, best practices, simple diagnostics SDK, and then some final thoughts. So in the old days, and by the old days, I mean pre-pandemic, the traffic on our platform was dominated by desktop browsers and iOS and Android native applications. Mobile browser usage, didn't even register. But as the pandemic hit and we saw tremendous growth, we also saw growth in support tickets. And one of the interesting aspects was the number of people that were trying to use mobile web, and in particular, the types of problems that they were encountering. So we spent quite a bit of time last year helping developers with issues on mobile browsers. And that's kind of where we're coming from with this talk. So, if we kind of fast forward to today, we see that Chrome still dominates the traffic on our platform. So this is looking back over the last 30 days. But you can see like the number 2 browser on our list is mobile Safari. And then further down the line, we see Chrome on mobile. And if we add those two together, and there's a few other smaller ones, we see about 11% of traffic on our platform is now mobile browsers.
And that's traffic on like for Twilio video.
Yeah, Twilio video.
And I guess there's a substantial figure there. So
yeah. And like it's grown from tiny numbers. So if we drill in one level deeper, you'll see that mobile Safari dominates at roughly 64%. Chrome on mobile is lower at 26%, and then we have Samsung, Firefox, and a few others as well at smaller numbers. Another interesting aspect is the number of VP8 codec usage, very high in relation to H.264, but we still see some H.264 traffic as well, and we'll talk about that a little bit later.
Okay.
So, why use mobile browser versus mobile app, right? With a mobile app, you're going to imagine it's going to be more performant. You get to decide which WebRTC version to use. You can patch it. You can add in, support for extra hardware codecs if you want. But the real reason to use mobile browsers is it's a low friction way for consumers to get onto video chat, especially for infrequent interaction. You'd be surprised the number of people that have trouble installing mobile applications. So, with a mobile browser, it's like one click and then you're in video chat. And I think we've seen over the last few years that the WebRTC implementation on mobile browsers has become very consistent. You can rely on it mostly. We'll talk about that a little bit later.
Yeah.
And then I think the other interesting trend is the use of appointment reminders by businesses, like either SMS or email. And if you have a link to the video chat application in that, then it's really simple for people just to click and go. So like, what are the top challenges that we see with mobile browsers? The first one is ownership of the camera and microphone, right? At any particular time, like who has the ownership, and then the kinds of problems that can cause, right? So symptoms is, participant cannot see or hear the mobile participant. And typically the causes are another application or tab has ownership of the camera or microphone. So maybe you were watching YouTube in the background and then decided to go onto video call. Get user media successful even when your microphone or camera are reserved by another tab or application. So surprise, you thought you had it, but really you don't. And then, get user media fails or, Bluetooth issues. I think everybody's had that problem. The next one is to do with backgrounding. So you're on your video call and then you get an incoming phone call or another video call. So the symptoms, the mobile participant is frozen. You know, you're chatting away and suddenly they stop and you're calling, hey, you're there. And then maybe they come back, but you can't hear them after they come back. So typical causes, you know, the incoming call or the media app has acquired the microphone or camera. Or the user has accidentally backgrounded the app during the video call as well. You know, that happens, especially with some of the older folks. Next one is just the general robustness of the browser media engine. So in general, you know, everything's working, but you see these edge cases of audio or video problems. You see some video artifacts. Typical causes, you know, a new operating system or browser version introduces a regression, mostly around audio. And then, you know, each video application and even the CPaaS vendors, you know, will use the browser APIs in a slightly different way, or the timing will be different. So that results in like some applications working fine and then others having problems. And then, of course, there's hardware codec issues, mostly H.264, but even VPH. So then last one, just general WebRTC support. So get user media maybe fails, or, you know, again, random incompatibilities and disconnects. So typical causes, the web view on the device doesn't support WebRTC, or the browser has some version of WebRTC, but it's not recent. So let's chat about best practices. So, you know, this is kind of the meat of the discussion. This one, you know, may seem obvious, but a lot of developers have a kind of allergic reaction to adding these kind of checks to their application. And then, you know, I've talked to customers where they're having a lot of problems, and I ask them, do you do any kind of pre-call testing? And they say no, because they don't want to introduce friction to their users. But I believe this can be done.
Are they worried that people will abandon the call or give up? You know,
they want to get people like into the, you know, the chat experience as quickly as possible, right? And this is kind of like a, you know, nuisance, so to speak. But, you know, I think you can develop these, you know, waiting rooms or pre-call areas that are kind of low friction. And, you know, at the very least, you want to be able to see yourself, right, before you get into the call. And then, you know, a little microphone indicator as well. So, you know, these are low friction ways with huge benefits. The next item is around background and foreground event handling. So this one can be kind of tricky. So best approach, when you go or when you become backgrounded, you want to signal the remote participant to update their UI so they can kind of see that you're on hold and that you're not like just frozen and you know, you've been disconnected or something. It can also happen that, you know, when you're backgrounded, that your audio and video tracks are paused, like the ones from the remote participant. So you want to monitor the playback state. To be safe, you should release the camera when backgrounded and reacquire it when foregrounded. You know, that will just guarantee that you have the camera when you return. On the microphone, it's a little trickier because you want to keep the microphone open when you go backgrounded. You know, maybe your mom is asking for the phone number of your uncle, and then you look up the contacts, and you still want to be able to talk. So then, you know, we have found that there are times where you may want to reacquire the microphone, and that these are the three cases, right? So media stream track transition to the ended state while backgrounded. The media stream track did not unmute on being foregrounded, or the media stream track unmuted but then emits silence, right? And
it's a lot of stuff to check for.
Yeah, I know. But I have some little bit of detail on detecting the silence. So some pseudocode. So in general, we use the analyzer node or a analyzer node, and then we just get the raw samples. And then if you see like a continuous stream of 128 or 0, then, you know, it's pretty much flatlined, and you want to go reacquire. So maybe check for like, I don't know, 200, 300 milliseconds and see what's going on.
Okay, yeah. So you pipe that over to Web Audio to do the checks, you know, similar, I guess, to like, you know, volume level, that sort of thing.
Exactly. That's it. Okay, so then, you know, Another best practice is just testing the beta versions of the operating systems and browsers. Just see if there's regression, see if you have any problems. With video codecs, your mileage will vary with H.264. Works great on some devices, not so good on other devices. You could just go with VP8 for everything except for the Pixel 3. So the best solution is kind of where you use the best codec for the best device, but that requires a bit of work.
You saw some specific issues on the Pixel 3?
Yes.
I guess is why you call that out? Yeah.
Yeah. So then we advise customers to use H.264 on the Pixel 3.
Oh, okay.
Next one is just decide what browsers to support. So it kind of depends on whether your customers expect everything to be working all the time, or whether the service you offer is free and you're trying to get the widest reach of users. So for the widest reach, just test that the WebRTC APIs are available and working. And then just a little bit on web views. So we encounter web views mostly in email applications. So the email has a link to a video chat, and then people click on the link. But within, let's say, Gmail, it'll open up in the web view within the application. Also for non-Safari browsers and iOS, that they use the Safari web view.
Yeah.
So on Android, it's been there forever, and it works very well. On iOS, there was no support from iOS 11 onwards, but thanks to the Apple team, iOS 14.3 has it. Last I checked, there was maybe around 70% of devices on 14.3 or 14.4. So we're almost there on that one as well.
That's not too bad.
Yeah. Just want to introduce quickly an RTC diagnostics SDK that we wrote and is available on GitHub. It's completely generic. It doesn't rely on the Twilio platform at all. And it has some of the best practices I've been talking about. So input audio device tests, input video device tests, output audio device tests. There is some network tests as well, but you'll have to bring your own turn server for that.
Okay. Yeah. So, but the developers out there can cut and paste this freely, I guess, or
yeah,
except for the turn server part.
Exactly. Yeah, they can fork the repo. Do whatever they want to do. So it'll hopefully get you started. So then some final thoughts. Mobile browsers are a low friction way to engage users in video chat. We have seen customers move to this from dedicated applications. There are some challenges related to mobile browsers, but they can be overcome. So what you need to do is verify that the input and output devices are working correctly. Handle background and foregrounded events, right? So that's the tricky part. Stay on top of the operating system and browser updates. If you see issues, report them. The more people that report issues, the higher the likelihood that they will get fixed. And then, decide what browsers you actually want to support and tell your users what your supported list is. So thank you very much. And as always, we can't wait to see what you build.
All right, thanks, Donald. I know there's a ton of questions that come in, so sorry, why don't you bring them on?
I'll try to sift a few of them out. Do you have a breakdown between iPad and iPhone on mobile Safari?
We can do it. I don't have it offhand. Yeah, we could do it. I would think the majority though is phones. Okay. Especially from the appointment reminders.
Okay, and I'll take one from the last ones. Any recommendations on dealing with screen lock while on a call?
I don't. Yeah, I'll have to check back with the team on that one. So we have a breakout session after this with some of the engineers, so maybe they have some ideas.
Okay. How do you handle incoming call notifications and availability?
Yeah, I think that's a tricky one. We have some customers who have used CallKit and kind of combined it with video. It's not something we support out of the box, so it's tricky.
Mm-hmm. And how do you handle if you're using the mobile web or mobile browser? How do you handle incoming calls in terms of vote notifications? Yeah,
so that's kind of what I was touching on. We handle it. We don't handle it as part of the platform. For programmable voice, we have more functionality. So what I've seen customers do is combine some of what we have in programmable voice with programmable video, and try to combine the two. But yeah, we don't support it out of the box.
Now, when I open, like you talked about going from Gmail and clicking a link and then you're inside the web view.
Yes.
But let's say I send an SMS to someone.
Yes.
That SMS, if I click that, will open in the default browser.
Correct. Yes.
Now, usually, if someone opens my app on Safari, I would tell him, use Chrome. And you would say, okay, and switch.
On Safari? Or sorry, on
No, I mean on a desktop. If I'm on the desktop, I can tell someone it doesn't work on Safari, go use Chrome.
Yes.
The same doesn't apply itself or end itself that easily or that well towards mobile. So it's not as if I can tell a customer, you're using the Samsung default whatever browser, go switch it. What do you see customers do in these cases with their applications?
Yeah. So it like we do have cases of customers who their end users end up using Samsung browsers, and some of them will say, yeah, you can use Samsung, and some of them will say, no, you have to use Chrome. So like at that point, you can either detect it in your app and try to provide some guidance and tell them that they need to use another browser. Like I think it depends on whether it's a paid service or whether it's free. For the paid ones, people are more willing to use one of the kind of approved browsers.
Okay. So last question, and I know that there are others, but this is the last that I'm going to ask. Is audio context still broken in Safari?
I cannot answer that question. Sorry.
Okay.
Maybe Ewan can talk to that one.
All right. Do we have any other questions for now? I think there's other things, but we probably can handle those during the Twilio breakout session. So, all right. Well, thanks so much, Donald. This was very informative.
Live streaming.
Just give the go ahead. All right, and we're back. So I mentioned earlier in the intro talk about some of the new emerging use cases, and this talk is going to be about one of the harder parts of WebRTC and audio in particular is conveying music. And a lot of you might be familiar with Dolby in that domain, the Dolby brand for stereo, but they actually have some interesting real-time communications technology in this area too. So I'm happy to welcome back Paul Bausted to talk a little bit about how to use WebRTC audio in music applications. Take it away, Paul.
Okay, thank you. So my name is Paul Bousted, and I currently lead product and technical strategy for Dolby's cloud offering, Dolby.io. So over the last year, the use of WebRTC for communications has grown very rapidly. And we're seeing WebRTC being used for much more than voice and video conferencing. It's now being used heavily for telehealth, education, and online events like these. And we're looking at these different applications and how we can improve the experience by optimizing audio and video capture processing to suit the use case. So why is it important to consider the application when designing your audio processing chain? Well, the communications and WebRTC community has been working on optimizing audio capture, focusing on voice for a long time, and we've got really good noise suppression, leveling, echo suppression techniques optimized for voice. Even within voice communication, you want to have different settings for different use cases. For point-to-point communication, you want to let more audio through as it gives you a feeling of presence. And in meetings or virtual environments, letting through too much environmental noise can be very disruptive and really leads to everyone just going on mute, which kills interactivity. These algorithms are great for voice, but what happens if you don't want to transmit voice? The current wisdom is really just to turn off all audio processing. In this presentation, we're going to have a bit of a deeper look at the music use case as an example of optimizing the audio chain, and we'll talk about the different music use cases, initially focusing on delay considerations, and then we're going to talk about how to improve music capture.
All right, great.
So, there are many different online music use cases, and playing music online together is desirable when musicians can't get together because of COVID. Online music lessons have also become very popular, and you no longer have to hire someone that's nearby. We're also working with social network companies that want to enable users to share music and play music with their friends and family, and even stream music to followers with a low delay to enable interaction with the audience. We'll start with a discussion of playing interactive music online because it's obviously the most demanding use case. Playing music together has significantly tighter delay constraints when compared to talking. Studies have shown that musicians need to be less than 8.5 meters apart to play together acoustically. This corresponds to a delay of about 25 milliseconds between the musicians.
That's pretty quick, yeah.
Yeah, that's right. They can be further apart, but you have to have some sort of low delay sound reinforcement system. When you get further apart, it becomes increasingly difficult and very unsatisfying to play together. In comparison, for voice, a delay below 150 milliseconds is ideal. But with voice, you can still carry on a conversation with hundreds of milliseconds. So to keep the delay below 25 milliseconds, there are a lot of things you have to consider. The audio interface delay includes both capture and render. And for native applications, you can get this delay below as low as 5 milliseconds if you use pro audio devices. But you're generally looking at 10 milliseconds for the very best consumer devices. But often it can be over 50 milliseconds. Within WebRTC, if you get everything right, I've seen people get it as low as 17 to 20 milliseconds, but it's generally a lot higher. The codec algorithmic delay. So the default algorithmic delay for Opus is 26.5 milliseconds with 20 millisecond frames, but you can get it as low as 5 milliseconds if you use 2.5 millisecond frames, but you're going to be sending quite a high packet rate there. Network delay itself will depend on your carrier and access technology. It can be as low as 5 milliseconds for fiber and 21 milliseconds for ADSL, based upon the data in the link below. In addition, you need about 5 microseconds per kilometer for transmission delay and a few milliseconds per network hop. The client will also have a jitter buffer to compensate for variation in delay so that you are continuously playing audio out of the speaker. If you're on a Wi-Fi network, your jitter buffer delay will generally be north of 25 milliseconds already. On a wide network, if the network is perfect, you can get it down to a couple of frames, but probably 5 to 10 milliseconds with 2.5 millisecond frames is probably the lowest you can get away with, but it's generally going to be higher. The key message here, while this use case is technically possible with pro gear and optical network setups, you're running at the edge with low jitter buffers, and you should expect audio issues and periods of time where the delay is above 25 milliseconds. So really, at the moment, you need to be an enthusiast to do this, and we don't see this as a widespread use case.
Yeah, it doesn't seem that's going to be practical for the general audience, at least.
Yeah, it's quite tough to get that delay down. You've got to look at each one of these different causes of delay to get there. So in the case where delay is above 25 milliseconds, there's some really interesting discussion in the reference below where musicians are able to cope with larger delays. For example, there are some music styles suited to a small additional delay, like playing in a laid-back style. And there are some kind of workarounds where you can, such as master-slave, where a master can play a percussive instrument and someone can play on top of it remotely. To the slave, it sounds like they're playing in sync, but the master hears the slave out of sync and has to ignore it. So really, over 25 milliseconds, you can't jam together online normally. This doesn't mean that people don't want to play music in WebRTC, and we're coming across a lot of interesting music use cases that do work pretty well for consumers. One person playing music at a time is still definitely possible, and you can have musicians playing to listeners and a voice conversation over the top of that, with musicians taking turns playing. This is very applicable to the music lesson use case. And there's a lot of social music use cases where people are sharing music with their friends. And also there are collaborative production apps where artists communicate while working on mastering a music track together. So what is the experience like using conferencing and WebRTC for music? Audio processing algorithms are usually on by default in conferencing services. And these algorithms are generally designed for voice and not great for music, as we discussed before. Noise suppression causes distortion and gaps in the music. Echo suppression can cause ducking or dips in audio levels when there is voice interacting over the music. And automatic gain control focuses on audibility and consistent levels and will really interfere with the creative intent of music. There can be long periods of quiet music that the musician doesn't want to be made louder. So in WebRTC and other conferencing services, you can't really tune these algorithms well for music. And if you Google, how do I get music to work well in conferencing apps, the solution is to turn everything off. Now, there are circumstances where turning off all audio processing algorithms does make sense. If a user has a professional setup with acoustically treated rooms, musical instruments wired up for good audio capture, and the user can listen to a live monitor of the output and adjust gains as needed. In these cases, the users want to control the experience through their equipment with no additional audio processing. However, for non-professional setups with normal rooms with no acoustic treatment and consumer audio devices using earphones, without any additional audio processing, this can sound thin and lifeless. And our work with consumers tells us that users want music to sound better. So we've been engaging with consumers to find out what they value in terms of music enhancement. In late 2019, we released a free app on the Apple and Google stores to start experimenting with music capture enhancement. The app allows users to record live stream audio and video. And they can apply a range of music enhancements to make the audio sound great without professional gear. So I encourage you to check out an A/B demo on the link below, or download the app and give it a try. This app's been a great way for us getting feedback from the community on what they value. Interestingly enough, we're finding it's being used in unexpected ways, and there's quite a few people using it to record voice. They like the way it makes their voice sound for podcasts and other applications. So we're now implementing these music enhancement features in Dolby I/O in our interactivity client SDKs. And to get this working in the browser, we're obviously using the browser to access the device and WebAssembly to implement processing, the processing chain that you see here. And also we're using the RTC data channel so we can make codec and transport changes to suit the application as needed. I'm going to go and talk through each of these blocks in the processing chain that we're implementing. I'm going to talk about what we're doing in each of the processing blocks and any related user interface considerations when building an application for music, and any WebRTC specific considerations that we're coming across during the integration. So for audio capture and render, it's important for us that we turn off all the device processing to get a raw microphone feed to our audio processing algorithms. Also, if we know the device ID, we can apply device-specific tuning, such as audio equalization to improve audio capture and render, based upon the characteristics of the mic and speaker. We can also decide to use the device or browser's echo canceller or our own. From a user interface perspective, you really need a control to select between music and voice modes. We're working on an automatic mode, but it's hard to tell what the user intent is, so it's important to have a switch anyway. It's also important to allow users to test the settings that they select before they start performing, so allowing them to play a small segment of audio and listen to the result is extremely important. For devices that allow low delay monitoring of the audio captured on the microphone through the headphones, it's got to be very low delay. It's important to expose a control to turn this on. This really improves the experience when you're wearing acoustic isolating headphones. It's good to hear what you're playing, and it disrupts it if it gets distorted by your headphones. Also, it's best practice to provide visual feedback on capture levels and also visual indications of clipping or any other issues, so the artist feels confident about the quality they're transmitting. One limitation of the WebRTC implementation is we don't have the exact device ID, the PID, VID. We just have a descriptive string. So it's actually difficult to make device-specific optimization. So we have to rely more on automatic means. With acoustic echo cancellation, in most cases, we assume musicians will want to hear or wear headphones for best quality, and will want to switch off acoustic echo cancellation. However, we know sometimes people will still need echo cancellation, particularly kids in music lessons. So we're working on optimizations for echo suppression in the music use case. Some user interface considerations here are, for consumer use cases, you have to have echo cancellation enabled by default. Otherwise, you'll just get howl. Otherwise, you need to tell, however, you need to tell the user that the best experience is with headphones and provide an obvious control to turn it off. Harsh fricative sounds like sh and th are a problem for both conferencing and music use cases with vocals, particularly close mic configurations. It's less important if the capture device is, say, a meter or so in front of you, but people often sing quite closely into the microphone on a device. So equalization, or EQ, is a process of changing the balance of different frequency components in an audio signal to change the characteristics of music. A static EQ has sliders for different frequency bands, and this can be hard to tune, and definitely hard to tune during a performance. So we've developed a dynamic equalizer, and this performs equalization on a per audio frame basis, adaptively applying gains in order to achieve a targeted spectral shape. We offer a number of equalization profiles that are specifically tuned to match a music genre. We also have a dynamic range compressor, which will reduce the volume of loud sounds and increase the volume of soft sounds in a very short timescale. In voice conferencing, the goal of dynamic range compression is generally to make the conference participants sound audible with a consistent average loudness to improve intelligibility. In music, the feature is being used for artistic effect and is much more active. We aim to enhance the presence of the audio and give it a much tighter dynamic range. And obviously this is quite tied to the dynamic equalization setting. So the different style of music you choose will have a different dynamic range control. So spatial widening, with voice communication, we render multiple voices in a conference called spatially to improve intelligibility with overlapping speech. This really allows for much more productive and engaging natural conversations. I spent time talking about this in the Kranky Geek presentation in 2019.
Yeah,
with music,
that.
yeah, I enjoyed that discussion. I quite like talking about the spatial stuff which we've been doing. With music, the aim is to upmix mono capture to stereo to create a wide soundstage. This makes it more immersive, but people also expect to hear music in stereo and hear music wide in front of them. So I'm going to finish with some takeaways. So audio quality is very application specific. With voice, you want to do things differently for one-on-one versus group communication. With music jamming, the #1 measure of quality is delay, and people are willing to deal with network-induced and CPU-induced audio artifacts to get there. In other interactive music applications, sounding good is the primary goal, and that's what we're focusing on here. The tools we're creating here can be used for more than music as well. We've got some customers, I said, that really like the dynamic EQ settings to change the characteristics of their voice. They like the perceived quality that they get. WebRTC's audio processing algorithms are really not suited to these non-voice use cases. They can't really be configured to be suitable for the music use case, and it's really best to turn them off. And we've shown that you can improve the experience by implementing custom music processing in WebAssembly. We're in the final stages of integrating this processing into our WebRTC communications SDKs. We're really interested in working with developers who have music or just innovative audio applications in general. If you want to talk to us, you can go to the link on the page here. We also have some free Dolby t-shirts to give away today. And there's a link to our virtual booth there as well. Thank you.
All right, thanks, Paul. Maybe we're running a little bit behind. Sai has maybe a short question.
Yes,
a quick one we can do.
I guess the questions here are quite complicated, so I'll ask this thing. This is because my wife is actually a dance teacher, and she tried instructing over these tools for the last year or so. It never works. Now, I think that music is even easier than dancing, because what do you do when the beat and what you see on the screen must be also synchronized while synchronizing both sides?
Yeah, that's definitely a good use case. And I think there's two ways people are addressing that case. One is sending the audio, so having a voice channel and then plugging in their stereo into the laptop and having a separate channel for music. But a lot of the small studios actually just want to play it through the speakers in the room and dance to it. And that way you actually it's much easier to get the lip sync because it's combined, and it's much easier to set up. And I think the thing we're finding is people much prefer something that's easy to set up but just sounds good. And that's ease of setup is pretty key.
Yep, that's a pain.
All right, we need to jump to the next session, but thanks so much, Paul. It's
Thank you.
I think very interesting for
Paul. There is a breakout room at the end for the questions that we couldn't answer, and for other questions that you want to ask, just go and join that room. And Paul and others from Dolby will be there.
All right, we'll see you all in just a minute.
everyone. We're in the last session of the event before the breakout rooms, and with me is Jan Skoglund from Google, and he's going to talk about Lyra. For me, that's a very interesting topic because it's a very new codec that just came out. So Jan, the floor is yours.
Hello, everyone. All right, as Syed said, my name is Jan Skoglund, and I'm here to talk about a speech codec that we just developed. And luckily for the world, we open sourced it. You might think, well, why do we need low-rate speech coding at this age? Because video would, and we have good communication around, and video would probably eat most of the bandwidth. So there's nothing left for, or nothing left. There is nothing much for compressing speech, right? Why do we need to do that? But that is not really true, because lately we've seen that there is a communication problem. For example, many mobile users are still on 2G networks. That's quite a lot, 1.5 billion people. And the same number, and even a little bit more, are on 3G networks. So they have very little bandwidth available for both audio and video. And another thing is these unlimited data plans that are, you have a high data rate, but then you max out and then you throttle to 64 kilobits per second. And 64 kilobits per second, that means there's like a 30 kilobits left for audio and video, and even less. So, and another thing that came up this year is this: when you work from home or anywhere, you will see, even in the best networks, there will be these kind of dropouts, and you wish, like during 5 minutes, that if you could just switch to a low-rate coder during this urgent times, so that would be best. So it is actually a real problem, and the question is, like, the science question we can have here is like, okay, all right, what is the lowest we can do then? How low can you go if we can just give all the efforts in the world? So this is something that people thought about already in the 50s. And so thinking about, like, you have a speech, but you have a speech recognizer that converts it into a text stream, like ASCII text, and then also some other things like who's talking and what mood that guy is or woman. And then also, like, if intonation, if like what do you want, like emotions go up and down. And then on the other side, you take this text and these kind of metadata about the mood, and you just generate speech. That is kind of the ultimate low bitrate codec. And the early estimates from the 50s was that that you can do this for English, you could do it around 50 bits per second. And a more recent estimate, because this comes up now again, because it becomes an interesting problem again, is that it's around 100 bits per second. It's if you want to squeeze out everything and then just start transmit it. The problem with these limits are that they need very long delay, and sometimes infinite per channel. That means that it's not very practical in a two-way communication, like voice over IP or conferencing. So practical speech coding, basically there are two classes. And the ones that are really low go to really low bit rates. The ones that basically I talked about in the previous slide, and the ones I'm going to talk about today are called parametric codecs, or sometimes called vocoders. That is, that they are speech synthesizers. There is an oscillator that generates speech waveform, and you transmit not the waveform itself, you transmit settings for this synthesizer of how to produce a speech sound. And by doing this, you can just be very efficient, because you just have to send over these parameters and you can quantize them quite hard. So you get very low bit rates. You can go down to 300 for the very typically, and up to, and they work up to about 5 kilobits per second. Sorry. The reason why we typically don't go higher is that these coders are completely limited to the model. After a while, you can give them as many bits as you want, but in the end, it's just you are limited by the synthesis, the speech synthesizer. That means that it doesn't really matter how many bits you set. The problem in the past is that these sound pretty robotic, but very intelligible. So they're used only today at very like narrowband speech applications like secure communications, where you have very few bits for the actual speech channel, and most of the bits go to encryption. So the other class, there is another class, luckily, they are waveform match encoders. You're not trying to mimic the sound, you're actually trying to mimic all the output samples. So you give it bits to mimic and try to follow the speech waveform. And the good thing with this is that the more bits you give to it, the better it comes. And of course, if you give it infinite bits, it will be infinite quality. So that's the good thing with waveform coders. The problem is that they break down because if very, very low bit rate, they can't really reproduce the speech waveform as well at low bit rates. But they have, sorry.
And today in voice over IP, it's like most of the codecs would be waveform based or parametric based?
Good question. Today in voice over IP, the typical more, I guess, in voice over IP conferencing, I would say all of them are using waveform match encoders. Even like Opus or AMR narrowband, even if they have some models in there, they're in the end of the day, they're trying to match the waveform. So, but they're used in a rate that is good for them. So like Opus typically right now, when we talk in here, it's like 32 kilobits per second. It's almost transparent. And sometimes in other type of VoIP scenarios, you go down to 10 maybe. So this is good. But now, if we want to go even lower, these guys can't do it. The only thing we can do then is like look at these traditional parametric coders, but they don't sound so good. But so the question is now, can we do better parametric coding? Can we have better synthesizers for these features that the parameters that we send? And the question is yes, thanks to the new AI that reemerges. I mean, there was AI for speech processing in the past, but now that we have more powerful systems, we can actually do something useful. And a couple of years ago, DeepMind introduced WaveNet. It's a speech synthesizer, text-to-speech, which we had remarkable quality using just a deep network, and where the produce one sample at a time, and that sample got fed back into the system and controlled by some other features, synthesize like speech, language, and sound features, and it could produce fantastic quality. It has high quality, but the price is, you see these deep networks, it's pretty high complexity, which was fine for experimenting and also the targeting cloud computing where you have data centers that can work. And we were looking into, maybe we can do this, we can use these kind of synthesizers, these really good oscillators to generate speech. The problem is that there are some differences already from the outset. We are not going to generate features from text. We're actually going to extract them from recorded speech. That's one thing that's different. And then also, we needed to work for more speakers, not only the few speakers that you typically have in the text-to-speech system where you train for just a few voices. This a phone should work for everyone. So we tried to look into that problem, those two problems first, with a WaveNet as a synthesizer, and we had a research experiment that went very well. We drove WaveNet with parameters extracted from a parametric coder called codec 2, and that was coded at 2.4 kilobits per second, and we managed to make a coder that sounded fantastic, or really, really good for those conditions. So that kind of spurred us further, like maybe we can do something practical about these things. Mm-hmm. The problem, of course, first is that WaveNet is astronomically complex. So first of all, we need to get reasonable complexity so we can put it on a phone, because that's what, for instance, Duo wanted it. To work on a phone. And luckily there are better, since WaveNet was introduced, there are newer architectures that are more efficient. So first we replaced the WaveNet with something called GRU, which is a recurrent network that is much more efficient. Secondly, we call a sparse model, meaning that we don't use all the weights in the network, we just use a few in a smart way. And the third thing that we did was to generate a couple of samples at the same time. Like we do 4 samples at a time, so this doesn't have to operate as often as another one would do. So we instead of taking 1 sample at a time, we produce 4 samples at a time. That's the complexity. Another thing that's different from TTS is that TTS is targeting high quality studio recorded speech. And the same thing we did in our first experiment. But in real life, you have background noise. So you really need to take care of that. And what we did to combat that was, first of all, we used features that were more kind of diverse. So we figured out we need spectral features, that the entire time frequency spectrum is better to use for this. And then the last thing we did was something recently we found that if you train with noisy speech, you get noisy speech even if you don't want it. So we introduced a loss so that we penalize unwanted noisiness when we train the network. And that gave us, in the end, a Lyra codec that operates at 16 kilohertz sampling frequency and uses 40 milliseconds frame rate update and 80 milliseconds frame size. And we quantize at 3 kilobits per second.
So it's a parametric codec that uses AI to reconstruct the part of speech to text, so to say.
Yes. So instead of so I can look here. So a generative, here is how it operates. A generative model, that's the synthesizer. It takes some speech features and produces a speech waveform. Those speech features, we are not generating them from text. We are extracting them from input speech. So you look at the left there, we take input speech as a time waveform. We extract features that are spectral features. It's like time frequency image here. You can see frequency in the vertical direction and time in the horizontal. Then we quantize them. We basically make them into a bit stream and then use this to drive this generative model, which is like a speech synthesizer. And since it's a parametric coder, it will produce a waveform, not exactly the same waveform, because we are not trying to mimic the waveform. If you look carefully, the input and the output, the waveforms are not exact. They are similar because they produce the same speech sounds, but they have no intention of being exact the same thing. But they sound pretty good.
Okay.
So we made this thing open source. And we put it at GitHub. We put it there as a library with a regular API. It's very easy to wrap it into WebRTC. The reason we didn't open source our wrappers was because our wrappers are very heavily tailored for Duo, and it's not very generic. So and we felt like that would take some extra time to make generic ones for the world. Since especially in this community, I think most people there know how to make a wrapper like I have here, how to call Lyra from WebRTC. So after this, what are we planning to do next? Yeah, the first thing we want to do is, right now, Lyra works on real time on slightly high-end phones, like all the Pixels and the higher end Samsungs. We wanted to work on a bit more than that. So we're trying to reduce the complexity a little bit more on our side to enable more devices. We are also looking into kind of presenting Lyra or making it operate at several more bit rates so that we can enable more use cases, not only these emergency super low bit rates. That is more of a long-term project that will take some time because it's really, really now focused on low bit rates with this synthesis model. But we're working on it. And another thing that we noticed is, even though we train with noise and make a good model that can robust with that, after a while, if there's too much noise, it breaks down. Less so than waveform coders. However, putting a denoiser in front of it makes really good quality. So we're considering putting a low complexity denoiser as a pre-processing stage, and hopefully maybe open source that one too. But another thing with open sourcing is, of course, we want community contributions, and we've been open source for just a short while, and there are already been really good contributions from the community. So thanks for that, and I'm open for questions, I guess.
Yeah, we do have a few questions already. Maybe I'll start with the easy one. Is this in production? Is it ready? Is this actually being used in Duo?
It's in production, yes.
Okay.
It's
wide scale production, or
no? It's running out as an experiment. We really don't want to just like throw into the water and see if it swims. So it's slowly introduced to more and more people. So, but it is already rolled out for a fraction of all the users out there.
There were a few questions came out. You covered it a bit in your last slide in talking about denoising, but several questions around how is non-voice handled? Like, what would happen if someone played music? What would it sound like?
Voice. It would sound pretty bad, but they would try to mimic it with all the speech sound it has in its repertoire.
Okay.
Because it's trained for speech with a little bit of extra. So yeah, maybe it learned how to make a flute, but not likely.
Okay. And since it's trained on speech, does it kind of automatically mute non-speech already? I mean, does it effectively have kind of a denoiser for non-speech sounds already?
A little bit, but not so much. We have trained with that too. We have another paper on that it's trying to just target clean speech, but feeding it noisy speech, so it learns how to kind of denoise. That wasn't as good as actually training with denoising first. So
okay.
So it has a little bit. I agree.
Okay. Well, but it's not really a something that you would use explicitly for.
No, but if you listen carefully, I mean, I've noticed that it kind of takes away a little bit of reverberation from rooms, or faint like fan noise. But that's basically all of its capacity. If you have like a dog barking, yeah, all bets are off.
Okay. And can you talk a little bit about the kind of the complexity, codec complexity? There's a specific question around the decoder complexity, but I'm also curious the encoding too. I mean, will this run? What kind of devices can this run on? Or what kind of overhead does it introduce? And
the encoder is extremely lightweight because it's just a spectral extractor, and then you quantize that simply. All the complexity is in the decoder, in the networks that generates the speech. And I mean, I think you're like I don't know the numbers, but it's several times real time on pixel phones.
Okay.
Okay. Well, I think we don't have more time.
Unfortunately, no.
Yes. So thank you. What we're going to do now is move to the breakout rooms. You should have that over email. If you don't, just email to info@krankygeek.com and we'll send you the links. You will be able to choose which room to go to, and you can switch in between. The speakers will be there to help you out.
All right, we're gonna put those links in the chat too, I guess.
No, it will be over email.
Just over email. Okay.
Yep.
So how do we go to? Sorry again.
That's for the sponsors. That's fine. You're off the hook.
Okay. All right. Yeah. Okay. So I guess this is a conclusion of our
our spring event.
All right. If you don't have those if you don't have the breakout sessions, email info@krankygeek.com.
Thank you for being with us today. It's been a long 3 hours or something like that. We'll have our next event in November. That one will also be virtual, and hopefully next year we will see you all in person again.
All right. Great. All right. Thanks, man.